I guess I should grade harder or something, a little bit harder. Just so you have to do the last homework, but it's too late now. No. I guess you guys need a break anyway, though. It's been like 5 years, like prison sentence. All right, yeah. Yeah, like usually if you got a job and you're gonna start work too, you want to, I don't know, it's a good time to kind of kick back a little bit. I guess. I mean, I don't really remember what I did. Basically, seems like the last semester wasn't really doing much. I think that's what I kind of vaguely remember. But no. Anyway, so this is this machine learning thing. It's based on this. This is a science paper that isn't the people that wrote the paper we're looking at, but this is from like 2018. So these are folded native state proteins. Like glucose oxidase is the one they're all popular, but this is the one that's in devices to check blood, like you test blood sugar with it. I think it oxidizes glucose and then changes the pH or something. You get a pH meter. You can read the glucose from that. So, so one problem is like, so that was originally like little strip devices. Now they're like insertable devices that you use. So basically those last like 10 days. And the reason is this glucose oxidase loses its, the same is true for these other proteins. They're all like active, I think, oxidizing proteins. So anyway, it's got a lot of functional groups. So when you in proteins in nature, there's a thing called a chaperone protein that will go with the proteins. So two proteins. One's the active proteins, one's the chaperone. The chaperone will kind of a lot of times they'll help the protein fold, or so they're like helper proteins, or they'll help it transport through a membrane, or in this case, it could stabilize a protein to thermal degradation. So they're thinking that the reason it stops working after 2 weeks is because of thermal degradation. So you can put a protein around it, or you could put something around it, it would protect it to this, or just in transport or storage, things like that. So anyway, so that's the idea. Like, so it has certain functional sites on the surface, like hydrophobic, hydrophilic, ionic, sulfide, like disulfide linkages, things like that. So the question is like, oh, say you could just, so you could design a polymer, a block copolymer, but not block. It's a random copolymer they're making, but it could be a block copolymer. So, and if you could put the right functional groups on it to match up with the surface functional groups, then it could like wrap around it, I guess is the way I envision it, but somehow interacts with it to prevent it from degrading. That's the point, right? So anyway, they take like these are acrylic groups. It's like polyacrylates. It's like polymethyl methacrylate. If this was an OH group here, that would be like PMMA, like plexiglass, right? But with polar groups on it, it's water soluble. So they have a bunch of different functionalities on that thing that they think might be useful for this. In other words, a sulfide. Well, they don't have amides here, but in the other paper they have tertiary amines and then amides and some other things. So they have 4 things, and they say like we could make this thing, then it could wrap around it and protect it. That's the main idea. So they published this paper in Science, and they showed you could kind of do that. But there's an infinite number of possible like components to this scheme, right? In other words, you can put anything you want. You can stick anything you want onto an acrylic group, and then and if you have a polymerization that you can do automatically, then you can make these things, right? So there's a paper. Let's see. All right, so let's see. Let's find the right paper here. That's a login. Where is it? Let me go back here. This there's actually a link to the paper and then you can't, they don't let you download a PDF, but I did a PDF of the, anyway, this is the paper from 2019, a year after that. And they have this machine that they bought at Rutgers. So this machine that does that synthesis. So this machine will make any block copolymer for you. It's got vats in it. And then you just tell it what to make and it makes it. It uses raft polymerization. I think one of the first papers we did was raft, just like a protected free radical. So you can make, it'll just keep running. Anyway, so they have the vats, it just shoots in, right, monomer mixture, and then it makes a variety of block copolymers, different molecular weight. So it's a polymerization that goes until it eats all the monomers. So it's a fixed molecular weight it makes. So you can control the molecular weight length, you can control the composition, like the amount of each of the components in it. And then you can make thousands of polymers with this in like a week or something. You can just produce as many as you want. It's making like, I think it makes like 100 at a time. So it's got a tray with little troughs in it. And it's got little zip, 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 puts the liquid in, shakes it, whatever temperature it needs to go to, and then the polymer's made. So it's pretty slick, right? So anyway, I mean, if for this task, it's slick, it isn't exactly, you wouldn't do this for mass production, but if you want to see, so they're showing like they can get monodisperse or narrow distribution of molecular weights. They can get any molecular weight they want. Composition wise, they can get what they want. So everything's nice, it works. So these are the things that they make it in these little kind of biological sample things, polyethylene, little tub things, whatever. I think you guys have seen those kind of containers before, right? Somewhere. They're in the labs anyway. Everyone has that kind of thing. I'm not sure what they're called, cuvette or something like that. But anyway, so that's that paper. Then the idea is like, let's see, what's the next one to look at? The Tamizi. So this is the paper that kind of is the parent to the paper we're going to look at. So this is where they take that machine. They use these acrylate polymers. So they have a sulfide, like a PEO kind of thing, hydrophilic. That's like polyethylene glycol. And then and they can vary the molecular weight of that thing. And this is a tertiary amine, another tertiary amine. This is with an amide and a ether, or just an amide. An amide replaces the ether and the acrylate. So they have all these are monomers, right? So it's going to polymerize from that bond, free radical polymerization. They just bought these from Aldrich. They can fill up their troughs in their little robot machine, and then just have it run and make any samples they want. So they make 500 samples. They could make as many as they wanted. So some question about so basically there are issues about like how many samples do you need? And in the other paper they go through extensively. So this is an actual research publication in the advanced materials. Then there's kind of a let's see if I can find it. Teaching paper from this, which is the one we're really looking at. So there's like kind of a, let's see here. Supporting information, Tamizi, that's that one. Automated synthesis, ML training paper, this one. I think I opened it, but I'll just open it again. So this paper, so this is like to teach you how to do machine learning using that other paper, using this paper, using the data from this paper. So this data is already put up on Google Colab, and they've already kind of have the routine, and they show. So what they do is they make the variety of these mixtures of the polymers. So 500, however many polymers they make mixed with each of these active proteins. Then they get this REA, which is how reactive it is after a certain length of time, to see if the protein protected see if the polymer protected the protein. Right. So the higher this REA, the better. So they have a single target parameter. So a lot of times you have more than one target parameter. Then there's ways to like funnel that down into like, so you say you have five parameters, you want to get it kind of fit into one parameter. So you have some function that connects the 5 to 1. Usually you're trying to reduce the number of parameters to 1. That would be nice. Or 2, right? So And it's described extensively in this teaching thing, this user's guide. Like he goes through, first this paper goes through like machine learning, what it is more or less, and then like how you would do it. In a little bit, it's a little bit confusing. It's not the best thing, but the nice thing is that at the end, they have an example that you can just run, you know. So, and you can run it in a web browser. So we should be able to run it here. Let me see if I can find it. It's called Gromley something. He also mentions a lot of things about like the programs you can use to learn machine learning. It depends. Like I think there's different kinds of people in the world. You know, some people are averse to this kind of thing, and some people eat this stuff up. And I'd say that's probably like 5% of the people. So nonetheless, it's good to kind of have a rough idea like what's going on. Trying to find the link here. He lists it twice, so he gives it right at the beginning. He does it again after. These are just learn Python, blah blah blah. I think it's actually in this first section, like section 1 here. See, this is just all he does is go through. It's like a textbook on machine learning, almost condensed version. But the problem is that the field is so flooded with terms that without knowing what the terms are, here, this is the thing, ML Colab. So you can just click that. It's also listed later on. Then this is actually, so this is inside colabgoogle.com. So it's using a drive in Iowa, supercomputer in Iowa. And then basically this is, so this Gromley has made this file on the supercomputer that you can use to just run, you know. And then if you want, so he's suggesting that you use this as a starting point to make your own machine learning thing. So with your own data set. So kind of start with this, then just modify this thing. And he's got every step described as if it was like a book. So it's kind of like a machine learning with one example, you know, which is that the example of these polymers protecting the proteins. So and he describes, there's a lot of text that describes whatever's going on. And then there's these things which are actually runnable, like you click that and it runs the program. This is what I mean by it's a script language. So it's just like a series of commands you put in, and then it does whatever it says to do. So it's going to, first it's importing the pandas is a package. It's like a software package almost. So it's a Python written software package. You have to import the math and the whatever packages machine. So all these machine learning things are packaged already and just import them. Right. So he's going to import it into this environment that he's created inside Google Colab so that he can use the code from that. And then this is the raw data, which is going to be in a Canvas file. So if you downloaded this to your computer, you could open it in not Canvas. See, it's a Excel file, right? So basically you can just open that in Excel if you wanted. He's downloading it. So GitHub is someplace where they're storing all the data. It's like a user opens place to store things, and then he's opening his data set. And then he reads the data set into this pandas program, into a data frame. And then the data set is this DF thing that he has. So it's just a series of scripts to do. So so the actual code to do what he's doing, you don't see, like you'll never see it. I mean, you could see it. So it's open source code, so you could see it, but you don't need to. All you need to do is run these scripts, which is already enough, right? In other words, run the scripts is good enough. So this is just importing the software to do it, and then actually importing the data and then loading it in so it could be acted on, right? So and then he does print the data set, and he shows kind of what the thing is. This would be like you open it in Excel, it would look like this, right? And it's got these columns, so it defines what the columns are, what their format is. So this is the pandas format, not the Excel format, but basically kind of what kind of numbers they are. And then they're for each, so it's got all the names of the acrylate monomers he's using. And then kind of the polymers, kind of what the compositions are, the things. And it's got also this REA, the reaction after it was fed through the reaction, how it came out. 623 block copolymers he used. So his machine made 623. He's got that data set in here. So this was all automatically made by a computer, the data itself. And then he's going to work with that data. So he's going to take a subset of that as a learning set. He's going to take a subset as a test set. So he's going to train his machine learning code, do the learning part, and then basically from that learning, he's going to see if it works with his test set. If it doesn't work, he's going to go back and modify the parameters he used to kind of fit the data more or less. And then an iterative procedure, get a thing that can predict what would be the best block copolymer, and then make that one with his robot and see if it worked. That's kind of the scheme of things here. So anyway, this goes through that. So it's basically shown here, like there's a robot making block copolymers, then those are fed into this, basically fed into another machine that does automatic sampling to see if these things are functioning. Right, so it's another automatic testing machine. So you have automatic synthesis, automatic testing, and then automatic data analysis that spits out and tells you how to do the next robotic synthesis to feed into the robotic testing to say if the thing worked or not. So that's the picture here. So it seems a little bit like something you see on a spaceship in a science fiction movie, like they're going to cure, you go into the Dr. Spock's or whoever, what was it, McCoy's lab thing, and he takes your blood sample and all of a sudden they know and cure your disease. Star Trek, right? In the 60s or whatever. So this is kind of the same thing. Like if you could miniaturize this thing, it would be Star Trek. And miniaturizing probably isn't too far off once you get the concept of it down. It's basically you go in, oh, you don't know what disease you have, the thing scans it, does every possible test on Earth, makes a guess at what the disease is, could be any, basically everything can be done this way. Like, and it's possible maybe to make it smaller than what he's got a lab full of this equipment. But anyway, so it's impressive, I think, to do this. So this is the actual paper. In the end, he comes up with these. So everything you get out of this is going to be totally different than anything you've ever seen, right? So there's a problem in nomenclature. So I have a list of like, I don't know, a gazillion terms that we know what PET raft is. That's the polymerization from the first paper. And then REA is the output. Did the protein do the function or not? What percentage of the functionality does it have? PPH, don't remember what that is. And so anyway, there's a bunch of terms that just show up, and particularly the shapely additive explanations is how so even when he gives his results, so he can rank, so this is the REA, so the third dimension, and this is the REA, how good it was. And the best one's yellow and the worst one's dark, which is kind of weird. So he can map out his proteins, his polymers with the proteins for these are each of the different HRP, and this is the glucose oxidase. These are the 3 different proteins. I think he does more than 3, right? But did he do 3 or 1? Anyway, so yeah, I guess he did 3. That's it. All right. In the other paper, they do 4, and then I don't know. Anyway, so there's 3 proteins and then a whole slew of copolymers, random copolymers. Then you can see there's certain features that show up. So he's mapped it against how hydrophilic, how hydrophobic, how ionic the groups are. And then see, everything is a parameterization from 0 to 1, right? So it's all computer language based understanding of it. And then, so you can see there's some some good areas to make these for this. And they're different areas for the different proteins, which is good. So it means it isn't just spitting out random information. It has something to do with the proteins. This is almost like a mapping of what the protein is like from the viewpoint of a copolymer. In other words, the copolymer is either happy or sad, so it's a 1-0 thing, the spitting out. So everything is 1-0, because the computer, right? But so basically you have this, it's interesting, like, so it's a different way, it's a different view of what a protein, native state protein looks like. It's like a picture of the protein in terms of functionality. It's interesting. It's like different. So like when you do scattering, you look at a structure from a different world of viewing it, like inverse space, right? And it's totally, doesn't look anything like what it would look like for you to look at it. And this is similar to that. It's like a functionality space to look at the thing, so this is a photograph of that protein in functionality space. This opens up a lot of interesting things, when you start doing this. Anyway, then this is where, this is a routine that he did. So iteration 1 is red. So that's his first, he puts in his first set of test samples. It went through the routine and it said, well, better look over here. That's iteration 2. The computer told him to do those measurements, iteration 2. He already had the entire array filled when he started. So he's already kind of got the answer, but he's running through this routine with a small subset. I think he uses 10 things each time. So it told him to do the orange ones. So he already had the data. So he got the orange ones, or he could have run the machine, gotten the orange ones. And then it tells him to get the yellow ones to fill out the map. So this is the sequence of events. And then I think exploit means that those are the ones, I forget what exploit means. I think those are the best ones or something or other. I think I asked you what exploit means, but I don't remember exactly what it means. Exploit knowledge of the chemical space. Or no, that's exploit. I know what that means. Dub the exploit round, the final iteration. Okay. So exploit knowledge of the chemical space. In the final iteration, dubbed the exploit round, iteration 5, we simply aim to maximize the REA of copolymers generated subject to the constraint that they are unique to within synthetic confidence. So you notice he doesn't, you notice that this thing doesn't cover all space because the stuff, if you get too hydrophilic, it gels. So he's got a region where he can't explore for each of the different native state proteins. So that's why there's a blank region here. Then the exploit, I guess, is what he predicts would be the best thing, which looks kind of like it's always pegged out at the side, except for this one, it's in the middle. So anyway, so that's kind of the way that plot is kind of simple. This one is not so simple. Okay, this one, so this is 0 to 100% of REA. So that's the how well it's reacting, right? And then this is a degree of polymerization. So this says, so, and these are for the 3 different proteins in color code. So basically, so you want to say, like, if I have a high molecular weight, do I have a high REA? Well, that's true of that purple one, but this green one, if I have a high molecular weight, I have a poor REA, right? Maybe there's another green one that's higher. Except, well, all of them have actually the same REA here, so the molecular weight didn't matter, I guess. And then the orange ones, so see how you kind of can read this thing in a sense. Like if you want to know, so supposedly you could track the 175 all the way through here and see with that molecular weight, and these are different copolymer compositions. These are each of the acrylic groups that he has shown in the first slide, right? I don't know which all of them are, but basically, oh, this is an amine. So the A ones are probably amines or something, but anyway, so this is breaking them on REA versus the composition of the, let's see, no, this is the composition of the copolymer, and then the REA you would have to figure out from here. This chart's almost useless. It kind of gives you an impression like there's a lot of information here, I guess, Then this is also REA versus the things, and then I don't remember what all these things are. Anyway, I ask you to figure out what all these are. The thing that's really most mysterious is this shapely value, which it's a way to rank. Let's see, it's a way to rank. So you can all these things you're going to have to Google. I mean, if you do the homework. Shapely values is good. Shapely values. So shapely, I think is, let's see. And basically Wikipedia is the best source. That's right. Shapely value. Yeah, so this is the guy. He won the Nobel Prize for this in economics, which is called the Nobel Memorial Prize in Economic Sciences, but it is the Nobel Prize. Anyway, it's a way to like if you have say you have a company with 10 employees and you want to know, and then the company makes like $1 million, right? Or maybe $10 million. And then like, how is an equitable way to distribute the money over those people? So the guy put in the capital, started the company, then he hires people all along, like 10 people or 100 people. And like, so what's the fair compensation for the guy at the beginning and the guy at the end? So Shapley came up with a way to do that. That's what this thing is, a mathematical way to determine that. Yeah.
So it's more slot for the donation.
Uh-huh.
I'm confused on that aspect because you said you have 100% hydrophobia and then it's about to create generation. But doesn't that mean just how much does that angular wetness for like young model, how much water this doesn't have to pretty much how much it doesn't cause light?
Yes.
So it doesn't need to be gelation per se, right?
No, but he made the samples and he knows they gel. So the gel ones you can't use. Because he's looking at a biological, like using these in a biological situation where you have water. So it's going to be like injected into a person or something. If it gels, it kills them. It's like gel is a non-go. So they aren't interested in the gel ones. So they didn't make them. They made some. They found out a gel. They made a borderline and said that's not within our range of looking. So there's some things that are just ad hoc. You're not going to test things that are a gel because they aren't of any use. So there's a lot of, so it's good. Like there's a lot of predetermination that goes into the thing that's supposed to be random. In other words, you decided that a gel isn't going to be good. A gel might be good in some circumstances. That's what this thing can't do. It can't say like, if you injected it with a gel, you would have cured cancer in the person. Like it can't figure that out. It can only figure out what you tell it. So there's certain limitations of this process, right? But within the scope of you're going to develop a new skin cream or something, this is exactly what you need. It can scope out every possible combination. Or you'd have to do like tests with people to say like, do they like the smell of it and things. Basically, it could figure out exactly what the perfect, most marketable thing is. Or even for sub-segments of the market, you could figure out and tune the thing exactly for almost individually. Right. So basically, there's a lot of things you could do with it. There's some things you can't do. Like it's not going to find out that a gel would have cured cancer because he already decided he's not going to look there. Right. So it's good to look at that. Anyway, so this can rank that. I think the reason it won the Nobel Prize is it ends up saying that the guy that owns the company can get 600 times what a worker gets, which is the current like compensation for most major companies. So it's like in the 1970s, it was actually 100 times. So it's gone up like sixfold, maybe because of this Shapley guy who won the Nobel Prize for saying that. It justifies kind of stealing money, I think is what it comes down to. Anyway, he got the Nobel Prize for it for whatever reason. Anyway, so in our case, so we have machine learning, and then you have all these different parameters you're getting out about how it's good or not. Like, is it good or not? And which things should you weight more or less? So they use this Shapley thing to decide what's most important. It's like, anyway, so there's a lot in that, I guess. So there's a lot in all of this. It kind of ties to things. So it's good to kind of figure out what these things mean. It's just a lot of terms, and some of them are complicated. Some aren't that complicated. Having a rough idea what the words mean is pretty important to figure out, because they'll just spit out. We're doing a CARTS analysis of the data to get to classify it, and then like you have to kind of roughly know what that is. like we're using a random forest process. So this example is going to use all these things. Put it that way. So just roughly Googling everything that they're going to talk about in advance is kind of useful.
So you do want us to review every one of those terms.
Yeah, until you get sick of it, or it doesn't have to be like, you don't have to be a genius about raft polymerization, but you have to it would be nice if you knew everyone's using it, right? In fact, like I'd say like out of the papers, 13 papers, maybe 5 of them use raft polymerization. It's basically everyone is doing that now because it's so simple. Like it's so simple and you get like monodispersed things out of it. So it's good to have a rough idea what that is. And yeah, just I'm not just see how far you can get. If it looks like it's too much, just don't do it. Just say like I did this until my fingers were bleeding and then I stopped. Show a little dot of blood on the thing or something. I believe you. But there's more. Like this is a small sampling. All right. There is some advantage to this guy though. He's got the Tasami. Let's see. Where is my training paper? Supporting information for his training paper is where did that go? Here is actually a list of words with definitions of them all. It's like basically he understands that like this is basically what you need to even do this. So you don't need to know how to do Bayesian whatever, right? But basically, if you know the word, they can find it inside the script, the Python script thing, and just use it. You don't need to know how it works, really. So what he does in this program is he tries 5 different so you have to parameterize the parameters. So you take the parameters and you have to put them into one number that you get out. So they have to be weighted. It could be a linear sum with weighting factors in front, or it could be some weird polynomial thing. So he does 5 different things of that, 5 different ways to kind of take a bunch of parameters and put them together and get a number out that's going to say good and bad, right? So it's easy to implement this. Like you don't need to know what they are. You could do 50 of them, right? And then the computer's just going to do it. And then it'll tell you which one is best at predicting the REA of this coupled protein copolymer thing, right? And then the one that works best, that's the one you use. And you still don't need to know what it is, right? So it's kind of a funny situation where you could find out what the best one was and then know everything about that afterwards, but you don't have to learn all 50, right? So it's kind of like it's like flying blind is what it is, but basically that's kind of how this thing is. Then this thing's just take that picture and say from the Tamazy thing, whatever it is. So you should, oh yeah, okay, so I was here, right? So these are all shapely values, it's kind of waiting to see which one is going to be the company president, which one's going to be a worker. So this shapely value is going to tell you which of these functional groups is most important in this operation. And then it might change how you would look at picking functional groups for your study. Like you might take the one that has the highest shapely value. So the negative ones are bad and the positive ones are good. And then these are all the samples that he ran kind of piled up. So anyway, like I said, learning how to read even the output of these things is confusing. You see like this shapely value is kind of like everything when you want to compare a variety of things that are going in. It's all statistics, right? But anyway. The nice thing is that like hopping fields in this area is easy. So if you do this for this biomedical application and you want to go to Wall Street and do the same thing for stocks, then this could be a list of Dow Jones Industrials and you still would use a shapely value to say which one is going to be the best to put in your portfolio. Right. So or you could use it to make skin cream, or you could do anything with it. So it's kind of like, so the nomenclature of how you read a graph is like changing rapidly. Like these numbers like shapely value suddenly become like really important to have a rough idea what it is. When you go to work and they're saying like, well, it had a high shapely value. It's like, what is that? Because you never learned that in engineering, right? Even though, so basically this nomenclature from these kind of like crazy looking people, whatever shapely is, are starting to become like like the main deal for whatever is going to happen. So it's good to kind of look at this and say, this is like a 3D plot of the shapely values. So you can somehow figure out what the best, like is, I don't know, figure out how the best, there's the 3 proteins in here. Anyway, just trying to figure out what these are, what's going on in these things. So I ask you to do that, to look through those plots. There's a bunch of them. That could also take a long time.
No, I was gonna say, do you know how that graph actually works? I was looking at that earlier and I was trying to figure it out.
I mean, I think it's the shapely values where you are going in and out. So the thing that's out furthest is best. Supposedly this helps you understand something, but I guess the ones that are out further, I don't know why degree of polymerization is like that. And it isn't for all of them. So basically the purple one likes to have a degree of polymerization is less important for the purple one than it is for the green and yellow. That's kind of what this is saying. In other words, what's the most important parameter here is what it's asking, given the results that it got. So I think for the green one, let's see, green and yellow are big in degree of polymerization, purple's less so. It's more interested in this SPMA, which is these people love acronyms, like everything becomes like so many acronyms. SPMA is just sulfate group on a acrylic. So that one dominates the whatever the green one was. Right. Green is the glucose oxidase one. So you put sulfate group, it makes the glucose oxidase run better. Yeah, I've seen this kind of plot also, like people, business people like this. They think it means something to people to look at it. And maybe it does to them. To me, it's really confusing, like I think it is to you, but basically, because this is being driven by a different group of people, not us, I think we have to accommodate them and figure out what they're trying to communicate in these things. Right. I mean, it's partly like biological tests are a lot of, like you do human testing and you have to get statistical accuracy in it, and there's a lot of scatter in the data. So you have to say from that scatter, can you say this is going to cure cancer or not? So then it ends up being a yes or no answer. So they're used to the statistical, and this guy's kind of a biochemist. So they're used to that kind of data analysis using statistical approaches, but it naturally falls into this machine learning too. So anyway, no, I don't know what this thing means, but I think you need to. I'll be dead by the time, so it's kind of like your turn. But anyway, just try to figure out, he throws this up like this is going to help you understand this complex system. I'm not sure it does or not. It kind of does in a sense. But if you so in the end, you're gonna have to do a decision based on this data. And it's such an amount of data that you need to have a new way to present it. That's kind of what happens here. Anyway, that's that thing. So figure 3, this thing. Figure 3. Yeah, that's figure 3. That's explain the experiment. That's like just figure 1. I mean, I said it, but basically he goes through it in figure 1. How he's going to make the this kind of cycle thing here, and then what his input things are. So you need to know those in order to do the last part. So the last part is just run the code. So I'm going to try to do some of that today, and then run the code by like doing a slight change to it and see if you get a different answer. That's D and E. So this D and E are kind of fun, except there's one step that takes 15 minutes where he takes the five reduction procedures, and then he runs all of them at the same time. So it takes 15 minutes to run. It's probably doing a lot of things. It's taking a data set of the 600 samples, it's binning it into different groups, and then it's doing the 5 different routines to weight each of this. It's like 5 different math functions to weight the things to get one number out. It's going to give them the answer. So anyway, that's basically this paper. his answer, so then there is something like he says, the revealing the mechanism. So what are you going to do with that? And then he says, like, I don't ask about this, but basically, this is more or less what he says he's going to do with it. So, and he says there's like different ways to relate. So that the prominent features in a protein, in a native state protein, are the alpha helices, so that the protein chain will spin around, or they can, the amide and hydroxyl groups can line up to pair, like plus ion, negative ion, and they make a sheet. So if you take, when you take eggs and you whip it into like whatever, then that makes basically predominantly beta sheets, which make it into whatever you call that, whipped egg. What do you call that? You make a pie with meringue or something, right? You whip the egg, make the meringue pie. That's beta sheets. So you take the native state uh, agulum or something, egg protein, and then when you whip it up, it breaks that native state apart, stretches the chains out. When they go back, they misfold and they make just sheets. So protein naturally is just going to make sheets. It's beta sheets. Like if you do anything to destroy it, if you put it into acidic or something, it ends up making beta sheets. That's a natural way. So that'll be really like when you have cataracts, your eyes turn white because it's beta sheets are forming in your eye. It's like beta sheet formation is kind of the source of a lot of problems. Anyway, so the mixture of alpha and beta is like a signature of proteins, and you measure that with this dichroism, circular dichroism spectroscopy. So it basically gives a number that'll tell you the amount of alpha and beta sheets in it. In the supporting info for this paper, he shows those plots, and he ties that in with kind of the functional maps of the thing. So he ties in X-ray scattering, where he gets more or less the size from it. So he throws out a lot of information from the X-ray scattering, and then he does circular dichroism. So these are all like pretty simple things to do. In dynamic light scattering, you get the hydrodynamic radius. So that hydrodynamic radius, rates of gyration, and this how much alpha beta sheet is in the thing. And then he maps that together. So how does that match up with his for the protein? How does that match up with his blockopolymers? That's kind of what he's talking about here. And how can it act as like a chaperone protein to kind of wrap around it? Like the science paper showed that, wherever it was. This thing. The polymer blockopolymers wraps around anything. All right, so got that. Right, this is the program. So basically this, if you click this, all right, so it's already been easier to do if you're a Google Mail person. If you remember your password. Which I don't. So I'm gonna run it on my computer. Which doesn't already has the password. Anyway, it's basically just clicking through this. It's already been done. It's just more or less to show you that you can do it yourself, and then go back in and change some of the parameters and see if it changes what the result is. So let me go over here. Or I could just look up my Google password. That would be easier. Bear with me. Not that I store my passwords on my computer. Comes up with my IRS password as news. It's like everything is there. close to what I guessed. Oh, didn't like that. What is the password? Oh, wait, no, it isn't. I changed it. Nope. Seems to be right. Right, that's it now. Okay. Open YouTube. I don't know why they think that this is easier to do.
I just started doing it because like some people started hacking like Google accounts. Cause like mine got hacked and then now I feel like the step like the two-step verification each time.
Yeah, but why YouTube? Why not just do it, call your phone?
I don't
I mean, call your phone would be easier. You have to, so I don't use YouTube all the, I mean, I use it, but I don't like. All right, so we're here, then I can run this thing now. So it just, it's not authorized by Google, run it anyway. So it's importing this big data set. Not onto this computer, but into the Google Colab server in Iowa, which they put there because Iowa has so much wind power. The electricity is like the cheapest in the United States. So it's kind of weird. All these computer banks are in Iowa. I mean, it's near Chicago, kind of, and it's like got free electricity. So it's like when they first did aluminum or airplane manufacturing in Washington State. It's because they had the dams on the Columbia River for cheap electricity for making aluminum, electrolytic, so electricity can put things in weird places. Anyway, so it just did, so it spit out the same thing that it had before, right? So it's kind of just showing you, it finally prints the data set so you can see what the numbers look like. And then you can find then you need to find the bad data points in this thing. So column 9, they can reduce this or something. Column 9, I don't see. Oh, you can get to it here somehow. Let's see, 1, 2, 3, 4, 5, 6, 7, 8, 9. So some of the values are missing in column 9, I think. The first observation, row 0, has a letter instead of a number. Oh yeah, it's got K here instead of a number. So he's just giving you, I think he put that in himself, but basically the data can have flaws in it that if you put it into the programs, it doesn't know that there's going to be a flaw there and it'll just crash out. So you have to clean the data. First step is to clean the data, get rid of the K line. So in other words, it's going through step by step every possible thing that could happen to you. So it's kind of the idea of this, but you can see the data set, first observation. Also looking at the output of info, we can see that this column is of type object instead of expected float. It's like when you go here, it says object for line 8. It starts at 0, so line 9 is 8, and then it's object. So it needs to be a floating integer for this thing to work. And then therefore we need to drop the first row. It has missing values, also convert the data. So the other option is you make up a value to go in there. So there's actually software in this package that will make up a value for that sample for you. It'll look at all the other things and figure out what the value should be or would be, or what give you maybe the probability of it being that number. So every kind of situation has already been coded, but you need to know all the words, like definition of all the names of everything to figure out how to do it. It's like the hard part is done, but the part of knowing the names of what you're doing and why you're doing it, those are the things you need to know. So the soft part is the only part you really need on this. I mean, you can do the hard part too, but right. So anyway, this thing will clean the data. So you run that and it cleans data. It got rid of that line. So instead of whatever it was, it's the second line. Like this is the 550 line becomes the first line. So 550 is the top line. So it's just, it shows and it did it by data set. What's the data set? And then data set, blah, blah, blah. To make a new data set from the old data set and then reset the index. So he just dumped a row on it. then print the data set. So all he did was drop a row. He didn't use any software to do that, but there is software to do that within the thing. But this is such a simple thing. He's just showing that you need to kind of have clean data. That's the point of that. And then once the data is free of impurities, then you want to separate the data set into the training set. So in other words, you got to have the ones that you're going to learn from, and then afterwards you're going to have like a test to see if it works, if your predictions work with the data. So he's got this. So sklearn's one of the things that you downloaded. So he's got. So you can sklearn as part of this software package called NumPy. It's almost like an application, right? So you're downloading the application first. It's got all the code in it. Then from the sklearn part of NumPy. So it's computer guys, so they name everything weird names, but then model selection, import the training split, and then the whatever. So he's gonna these operations will just split it into those two parts. So the method of doing that's already been figured out, and it'll work for any data set that's in some kind of format with titles and numbers up to 622. Right, so anyway, so when he's doing this, so from and then X data set, so he's got REA as a number that he's interested in. So he's only extracting parts of this thing. He's not taking the whole data set. He's only taken the glucose oxidase and the how good it performed columns. And then that's the Y data. The X data is the let's see, what did he do here? Anyway, I think you're just gonna have to the idea is read through these things and figure out what he's doing. And then just it's asking you to do describe. I mean, what you have to do is do what I'm doing and then describe each of the steps of the thing, like kind of the way I'm describing it in as shorthand as possible. Like not his long thing, but just summarize kind of whatever's happening, just for a rough idea. Again, yeah, if this is taking you too long to do, then bail on it. You might enjoy doing this, You could definitely do this and drink a beer at the same time. It's not like it's gonna, and all these things are Google search or web search, Wikipedia search, Or you can use his prompting thing for these too. So, and if you wanted to, you could split this up. I don't know. I mean, anyway, the idea is just to get a feel for what's going on here. That's the main point of this. Should you be more afraid of trying to do this or less afraid? Or does this mean something that you could do? Or is it something that I absolutely know now I can never do this, So get to that point would be good. I hope that the point is, and this doesn't have to be such a big data set, it can be just small, there's examples on the webpage. If you look at the thing on the tires where they just use tan delta, which you just measure with the rheometer, and you get G double prime over G prime, you get tan delta, and then get it as a function of temperature. And then, so they just have one number and then temperature. So they only have, and then they have a bunch of tires they look at something. And then the output is wet grip and wear, So basically it could be a small data set like that. I mean, they have I think they have 40 tires they look at. That's one of these examples. One's high density polyethylene. And I think they're just looking at the crystallization temperature versus the molecular structure or something like that. So there's only a fixed number of data points they have. They're trying to predict what would be a better polymer. So it doesn't have to be this huge 600 point with all these 600 in each of the measurements they do. So if you multiply by the 9 columns, so 600 times 9, whatever that comes out to, 3,000, whatever. So anyway, these other things are there's 50 numbers, so it isn't so big, and they can still use it. So, but this is a good one to look at because he's got it totally spelled out in his mind. In his mind, everything is totally set up here. But
Is that zinc or that Romley link? Is that in the paper or is that in?
no, I can put up in the links. but it's in the paper. It's in the first section of the paper. It's in both papers, so it was in the thing before. So if you go to, right at the beginning, let's see. No, it didn't do anything. And you, here, so it's the first section, at the last line of the first section, I think. That's the second section. Now, maybe if you just say Gromley. Oops. Not how you spell it. Gromley. Oh, Gormley. That's an interesting. No, I thought it was Gromley too. Gormley. Gormley. Oh. Yeah, this is the training thing, right? Yeah. Let's see. It's got Google in the name, so Google should find it. Nope. How about .com? Found a .com somewhere. Let's see, it's in here somewhere. I mean, I found it. That's where I opened the thing from, but no, this is the wrong paper. That's why. This isn't the one we want to know about. We want to know about the one, not that one, not this one, right? So if you go into the first section, so it's right there. So it's on page 142. It also is given somewhere else in this paper, but basically that's the easiest place to find. Section 1, just click it, and then it's just like go through this thing. And I think when you're done with it, you won't know exactly how to do it, but basically maybe you'll have a little bit better understanding of like what people are doing in this area. And anyway, so if you again, like if you feel like you have to bail on this one, like just kind of go give it some kind of effort and just say that that's it, but I think I went through the whole thing. I mean, it's kind of interesting. And I think if you do it twice, you'll have a better feel for it than doing it once. Because the second time through, and if you change some of the numbers and then see that it doesn't exactly change anything when you change those numbers. So like it's just changing the sampling, how he does the sampling on the thing. So
What's it currently?
I think it's like 20, and this goes to 2,000 instead of 3,000. It starts at 20. So it's just slightly changing the numbers. You can do more if you want, I mean, but basically one step of it takes 15 minutes. So the rest of it it's just click, click, click. But the one step is 15 minutes. So, yeah. All right. Yeah, we're over anyway. So, right. Good. Yeah. Yeah. And they say that like, so a lot of times what people do, and he does in here too, is you smaller groups and you see if you get the same answer for all the other groups. So you have the big set, you get an answer, and then you separate into like 5 small sets. It's done in this thing, and then compare what the answers are. And then you can make it even smaller so you can get a feel for like what's a valid, how much data do you actually need to collect? Like, are we overkilling this thing or do we need more, So anyway, right.
I have a question. Like, in comparison to like the other homeworks, like how much is like the final? Like, is it like the same?
It's listed. No, it's like 5 homeworks.
Okay.
I think it's listed on the webpage, but I think it's 5.
Okay.
So it's a lot. Yeah. Yeah, you have until the end of finals week. Yeah. And it shouldn't be that bad. You can look at the old ones up there. I mean, it shouldn't be too bad. Like, so, and if you need more time than that, like I can give a grade and change a grade after if you want to do it. You know what I mean? Like, so
I like friends, but I'm not too worried about your class.
yeah, don't worry about it, but just if it looks like you need more time, like I'd take it any time ever until you have a year.
Okay.
Put it that way.
Okay.
Like after a year, you have to do something, I think, but
Sounds good.
yeah, right.
Okay, thank you.
All right.
How does it work for, like the undergraduates again, for final?
If you're taking it for grad credit, you have to take it. If you're an undergrad, you don't, all right, if you're an undergrad and not a senior, you don't have to take it. No, you have to take it. If you're an undergrad and not a senior, you have to take it. Yeah, so, anyway, you can also calculate and see if you need to take it. That's the other thing, you know, like you can figure out like what it would end up being. It's possible that you don't need to take it, because if you're taking it for undergrad credit, you only need a B. So you might already have like what you need.
You know what I